Hi, I'm Tahir Ahmedi. My colleague is Pedram Agand. This work is supervised by Mochin and Anjal Kalim. We are going to present a new probabilistic approach for modeling human navigational intent using time to reach analysis and Bayesian filtering. Modeling human navigational intent involves estimation and prediction of future human states, possible goals, as well as intermediate states where the actions result in a path to the goal. As you see in this graphical model, our proposed probabilistic model of human exploits three parameters, a discount factor gamma, model confidence beta, and goal itself as theta. The arrows show the conditional dependency of the parameters of the actions and states. Our contributions compared to the baseline include using augmented states, a TTR-based Q function, a human deterministic index inspired from reinforcement learning, and using particle representation for goal and human states. Because analytic solution is interactable in four-dimensional state space, we use pre-computed time to reach values as a reward to calculate the utility of each state and action pair. Then we use a transformation of the original TTR values to the new goals in an online way. Here you can see how the underlying TTR-based Q function decides the optimal path to the goal given an initial state. You can see the different actions around the red circle showing the human state, and you can see the green arrow as the position and heading of the goal state. We use these generated synthetic trajectories in the first set of experiments for the evaluation of our predictions.
Thank you so much. My name is Pedram again. Right now, we want to talk about the prediction step. As you can see, in this step, we are going to, before we actually observe the actions, we need to update our latest available, we need to update our probability of different actions. And so we are going to use this formula. The Q function is obtained based on the transform and discounted TTR that we have talked before. For the updated state, after we observe the control function, what we are going to do is that we are going to adjust the model parameters, which was the beta, theta, and gamma. The updating rule for these parameters are completely the same. The only difference is the interchangeability of the corresponding parameters. So here we want to talk about the particle filters for goal state and human state. As we talked before, we try to use the particle filters to represent the probabilistic modeling of our goal and the human state. For goal, since the human can actually change his goal, we consider a parameter called mu to determine whether to choose from a predefined set of goals or choose it from the previous goals that we have. In addition, in order to obtain the probability of the state, we need to use our graphical model and the relation from the Bayesian approach using the relation that we see on the bottom left. For the particle filter in the human state, since we don't have the current control input of the system, what we do is that we actually draw some sample control inputs from the different set of actions, and then based on their probability, and then we plug in into the dynamic equation of the system and define the state of the human, and then we are going to compute the difference from the measurement to obtain the corresponding weights. In here, you can see the result of the particle filters for the human state and the goal state. The solid blue line show the ground truth, and the dotted red line show the weighted average, and the black one show the particle filter. For the goal state, as you can see at first, the different goals, which is shown by blue by green circles, are dispersed, but after some time, they're going to converge to the true values. In this slide, you can also see the different results of the human in the time. The red line actually showing the human movement, the ground truth, and the blue lines is showing the prediction, one step ahead prediction of the human. The green line, the green dots actually show the particle filter of X, and the purple arrows shows the corresponding particle filters at each time. As you can see on the displacement error table, the different result RMS error for the particle filters and mean average is shown, that show the particle filters can actually outperform the mean average in some sense. For more information, these are the context information. Thank you so much.